Hello everyone. Thank you for joining us today. It's a special day for us. After I became dean last year, Librarian has been a mentor over the years in Pittsburgh, asked me how things are in Doha. I said, weather is nice. I don't have space problems. I don't have money problems. I said, the thing that I really miss is faculty is young. I miss the fighting with the senior faculty in Pittsburgh. I said, well, we got to get some senior faculty to Doha to keep you healthy. And then he volunteered this course. Raj, for those of you who do not know, was the second dean of School of Computer Science. He hired a lot of people over there. So the people he hired, he could send them a memo and say, why don't we go to Qatar? And they're likely to say, okay, instead of saying, we'll think about it. So this course emerged, a special course with very senior people. In addition to this course, of course, we have another one on vision taught by Thacker Kanade. And next year we will repeat these courses. It's important that we have senior people from North America here, from Carnegie Mellon. We wanna maintain the Carnegie Mellon culture here and have some mentoring for our young faculty. The speaker today, Dean's Lecture Series, is a very, very special person. Many of you have heard him, of course, and they read the write-up about him. Chuck Thacker, of course, the Turing Award. Undergraduate in physics from Berkeley, as it is in the write-up. He joined Xerox, which was headquartered in Connecticut, Northeast America, had a research group in California. Wise decision. It was all PhDs over there working. They didn't bother them all day. I'm the chairman of Xerox. At one time was Paul Allaire, an alumnus of our business school at Carnegie Mellon in Pittsburgh. So Chuck joined that group over there. He was a founder of the Systems Research Center of Digital Equipment Corporation. Younger people don't know what DEC is. We grew up with DEC, of course. The mainframes at the time, before PCs and all that. Then in 1997, he joined Microsoft Research to help establish Microsoft Research Cambridge. His contributions to the field has been recognized widely, inducted as a fellow of Association for Computing Machinery, and in 2007 won the IEEE John von Neumann Medal for a central role in the creation of the personal computer and the development of network computer systems. And as I mentioned earlier, received the ACM Turing Award in 2009. I used to hear about Chuck as a young PhD and young faculty member at Carnegie Mellon. Never had the pleasure to meet him before, so it's a personal pleasure to host you here. We're delighted you came. And here is Chuck Thacker to talk about challenges for computing in the 21st century.
Well, thank you, Dean Devise. Well, it's a pleasure to be here today. Let's see if we can reorganize this just a little bit, so otherwise I'll walk into it. It is a pleasure to be here in Qatar today. I've never been in this part of the world, and I'm enjoying it immensely. It's a beautiful place. One of the things you have to understand about me, I'm not a senior person from CMU, which demonstrates Raj Reddy's ability to reach out to the thousands of people that he's influenced in various walks of life over the decades and snag someone out of industry to come here and talk to you today. I found over my career that it's been very difficult to predict the future. People who try to do it generally wind up being wrong. And I thought today that I would look back at some predictions and challenges that were made by an old friend, Jim Gray. Jim Gray received the Turing Award in 1998 for databases primarily. He was one of the preeminent founders of the relational database community. And tragically, Jim was lost at sea in 2007, so he never was able to see how his predictions and challenges came out. He was actually, in his Turing Award speech, trying to sensitize people to the need for additional government support of research in various fields, including computer science, and primarily to improve education. That does not seem to be a problem here, but in the US, as research budgets shrink, academics are beginning to feel the pinch. So he said that he posed 16 challenges, and he gave the properties that they must have. They've got to be simple to state, and it can't be obvious how to do them, because then they're not a challenge. It's just getting the engineering right. There must be clear benefit to the solution. And progress and the solution are testable. And these challenges can be broken down into intermediate steps, each of which you can look at to determine how the progress is going. So I went back and I asked, how have we done on some of these challenges? And I wanted to share my observations on that with you today. And in addition, I'll add some new problems that have come up in the last decade. First challenge, devise an architecture that can scale and grow the system without limits. Now, we've done fairly well at that one, because when Jim posed this challenge, the internet was in its infancy, and now everyone is on it if they want to be. Semiconductors, we've done very well there too. The integrated circuits that we have today are between 1 million and 1 billion times faster or larger or denser than the ones we had at the beginning. Magnetic disks are even more impressive. You can now store every bit that you receive during an entire lifetime on a single disk. Some of these technologies are running into physical limits. The thing that I always say is the basic problem in computing is that atoms are too large and light is too slow. And we're running into atomic limits, and that is going to change the way we do computing in the coming years, unless some very new technology comes out of the physics labs. Challenge 2 was pass the Turing test. Now, Alan Turing, who is one of the founders of our field, said basically, this is a paraphrasing a bit, he said, a computer is intelligent, or can be said to be intelligent, if you have a phone conversation with it and at the end of a half an hour, you can't tell whether it's a human or not. And we haven't done so well on this one. We still don't have machines that could reasonably describe in any way as intelligent. And that's not too surprising, because Turing didn't actually know what cognition is, and modern cognitive scientists don't either. So it's not too surprising that we can't actually build a machine that is conscious in the sense that we would understand it among ourselves in this room. But maybe that's not really the important thing. I mean, if you think about it, we use tools all the time. And a tool can be valuable even if it's not conscious. I don't care if my hammer is conscious and I'm building a shed in my backyard. What I want is a good hammer. And one of the things that we do have in computing is very good hammers on a lot of problems. His challenges 3 through 6 were sort of connected. They were hear as well as a person, that is, do speech translation into text, speak as well as a person, translate text to speech, see as well as a person, recognize objects and behavior. We can do that, I believe. One of the new things that's happened in the last roughly 10 years is that machine learning has had a resurgence in computing. Machine learning is also called artificial intelligence, and there have been several waves of artificial intelligence over the years as computing has progressed and as computers have been able to run bigger and bigger programs. The first wave was sort of pure artificial intelligence, and that was a flop. And then the second wave was rule-based artificial intelligence, and that was actually a flop. And a few more tries resulted in what we have today, which is called machine learning. And machine learning is basically, the definition is up there, the one that I actually like. It's the science of getting computers to act without explicitly programming them. Normally you have to tell a computer not what you want done, but you have to tell it exactly what to do on a step-by-step basis in order to get the result that you want. We have computers now that don't need that. We have things like the Google self-driving car, which can build a model of its environment and move about in it in a way that is as best we can tell after 500,000 kilometers of use, perfectly safe. And if that works out, it's actually going to change the world, because it will mean that we can invest less in, for instance, public transport, because the roads will be able to carry 5 times as many cars, for instance. Microsoft's Kinect, built in the context of a video game, it's been used for a lot of other things, including things like telesurgery. Kinect can actually model the user and can actually do the third thing, which is speech recognition a bit. Jim also mentioned illustrating as well as a person, and there what he was thinking of was graphics. And of course, we can do that now. We can have photorealistic graphics in real time, usually used in video games, but more and more used in movies. I mean, movie actors are probably feeling very nervous because there are many movies that we watch today that have no actors whatsoever, other than the programs in the computers. And they can capture the attention and awards just as well as human beings can. So I think some of these were in pretty good shape. And I'd like to show you an example. This was from a conference in China in October of just how well we're doing in this area. Could you roll the video, please? This is Rick Rashid, who's the director of research at Microsoft.
I want to come back to the topic of natural user interfaces. One of the most natural interfaces for people is human speech. And for the last 60 years, computer scientists have been trying to find ways to understand and recognize human speech. Now, in the beginning, when people first started tackling this problem, they looked at it largely as a pattern matching problem. And the earliest systems attempted to take the waveforms that came out of a speaker's voice and match them up to waveforms that they knew represented certain words. Unfortunately, that approach is extremely fragile. Partly because everyone speaks differently, but also even a single speaker will often say the same thing differently depending on the other words or the context in which they're speaking. You probably already noticed me doing that. Now, in the late 1970s, there was a major change in the way people decided to do speech recognition. This is work being done at Carnegie Mellon University. And the idea was to use a statistical modeling technique, in this case hidden Markov model, to make to really be able to take a lot of data from many speakers and produce more robust statistical models of speech. Now, that was a huge improvement. And over the last 30 years, speech recognition systems have become dramatically better than they used to be. They still make a lot of mistakes. But in limited domains, it's possible to do very successful speech interfaces. So, for example, in the United States, when I call my bank, I'm talking to a computer, I'm not talking to a person. The computer can answer simple questions about my bank account, or if necessary, it can connect me to a real person if I have a significant issue that I want to discuss. I'm sure you've heard of Apple's Siri products which answer simple questions. Microsoft Connect has a robust speech interface that allows you to control the interface, and it even allows you to issue commands in the middle of games. Still, these systems have a lot of errors. And the error rates for arbitrary speech have been in the 20 to 25% range. Well, a few years ago, researchers at Microsoft Research and at the University of Toronto came together to develop another breakthrough in the field of speech recognition research. The idea that they had was to use a technology in a way patterned after the way the human brain works. It's called deep neural networks. And to use that to take in much more data than had previously been able to be used with the hidden Markov models, and use that to significantly improve recognition rates. So that one change, that particular breakthrough, increased recognition rates by approximately 30%. That's a big deal. That's the difference between going from 20 to 25% errors, or about one error out of every 4 or 5 words, to roughly 15% or slightly less errors, roughly 1 out of every 7 words, or perhaps even 1 out of every 8. So it's still not perfect. There's still a long way to go. But I think you can see that we have already made a significant amount of additional progress in the recognition of speech. Now, one of the problems that we've also been trying to solve for 60 years is machine translation. And again, in just the last few years, the combination of statistical techniques and big data have allowed us to do a much better job than we previously were able to do in being able to translate web pages or other kinds of information into other languages. For example, today, Big Translate, which is Microsoft's translation system that comes out of Microsoft Research, Big Translate translates millions of pages a day for users into their native language. It's an extremely heavily used service. Now, if I want to have what I'm saying be translated into Chinese, we can take the text that comes from my voice and put that through a translation system. It really happens in 2 steps. In the first instance, we take the English and we convert it more or less word by word into Chinese text. And I think pretty soon we may see that up on the screen. So what happens is we're basically taking the English text and pushing it through the translation system. We then have to reorder that text in Chinese because the word order in Chinese is not the same as the word order in English. To produce something that begins to resemble something that a Chinese speaker might say. So now we're taking the things that I'm saying and we're converting them into Chinese text. Now, the last step that I want to be able to take in this process is to actually speak to you in Chinese. Now, the key thing there is we've been able to take a large amount of information from many Chinese speakers and produce a text-to-speech system that takes Chinese text and converts it into Chinese language. And then we've taken an hour or so of my own voice, and we've used that to modulate the standard text-to-speech system so that it would sound like me. So what you see now is the result of that change. I'm speaking in English, and hopefully you'll hear me speak in Chinese in my own voice. Again, the results are not perfect. There are in fact quite a few errors. 结果并不完美。There's much work to be done in this area. 在这方面有很多工作要做。So this technology is very promising. 用这个技术很有希望。And we hope in a few years that we'll be able to break down the language barriers between people. 数年后，我们希望能够打破人类之间的语言障碍。Personally, I believe this is going to lead to a better world. 我个人认为，这将导致更好的世界。I hope you enjoy the rest of the presentations today. 希望今天你喜欢其他的讲座。Thank you.
So I think every time. I think Jim would have been gratified to see that demonstration because I think it demonstrates that we're very, very close to solving machine translation. And I agree with Rick that when we do have it, it will lead to a much better world than we have today. So Jim's 7th challenge was a copy protection scheme, and that's effectively been solved. Jim didn't see Amazon or Apple or Netflix when he wrote this challenge, but they all do this. Now, the solutions that they have chosen are not perfect, but one of the things that you have to understand about computers is we expect them to be perfect, but the question is why? We don't expect other people to be perfect. And so the solutions that have been employed for copy protection and intellectual property protection use the same tools that we use in the real world to protect our valuables, which are things like locks and police and courts. And that's just fine, as long as doing the things that Amazon and Apple and Netflix do is sufficiently reliable that they're happy to do it and the customers are happy to buy it. That seems just fine. Challenge 8 was remember everything and return it. And as I mentioned in my opening remarks, we can now store everything on disks. So search engines haven't quite solved this problem, but everything that we get is digital, and we can store it, and we can index it, and then we can get it back. And some people do this, and in fact, you'll probably hear when Gordon Bell is here in a few weeks, his approximately 10-year pursuit to digitize every bit of information that he has received in his life. I'm not quite sure where it's going, but he wrote a very interesting book about why you might want to do this. I don't quite understand it, but Gordon is an interesting guy, so I have to believe it's important. Technically, I think this is solved. Economics and policy, well, that's another matter. 9 through 11. This was the Librarian. This challenge was based actually on an article that was written by Vannevar Bush in 1945 called As We May Think. It was published in the American magazine, Atlantic Monthly. And it actually described, more or less described accurately, a search engine of today, although it was 1945 technology. But it became the inspiration for several generations of computer scientists, including myself, in the things that we tried to build. Doing the same kind of things that search engines do for images and pictures and so on is a bit harder, but it's perhaps not as important. Most of the core information that we get does not come at us through our videos or our pictures and so on, but through text. And today I can use a search engine to find expert human commentary on essentially anything. So why do I need a computer to do it? Now, of course, the human may be wrong or may be lying to me, but I have to be selective. I mean, just as I'm not likely to use Wikipedia as a primary resource in a scholarly paper, it's perfectly okay to use Wikipedia to find all the references and then check out the scholarly, check out the original sources. Simulate being in some other place, either an observer or a participant. Telepresence. This is almost solved, but the difficulty here is that the solutions have to be standardized. Everyone needs to do the same thing. We have things like Skype, which will do a fairly good job at this, but they don't interact with some other systems that exist in the world to do the same thing. And so it will probably take a while for this to become real, but if it does happen, it will actually change things. And in fact, if we had this technology today, I wouldn't be standing in front of you. My avatar would be standing in front of you, and I would be in Palo Alto, not having to spend 16 hours on the airplane.
And it will be midnight.
That's right, I would not be lecturing at midnight. Given a specification, build a system that implements the spec and prove that it matched it. And do it better than a team of human programmers. We can't quite do that in software. And the reason is that software engineers don't actually like specifications. They like feature lists. And they go and implement features, and then we have large amounts of software that is just expanding and growing and providing a variety of possibly unrelated services. One of my old mentors, Nathan Myhrvold, has a law about that. He says software is just like a gas. It expands to fill the available volume. And the engineers in the last 50, 60 years have provided enough volume for software to expand far more than any of us thought would happen at the beginning of our careers. On the other hand, hardware people actually do this today, and it works out quite well. We use specification languages to write specifications. We model check them to determine the resulting artifact is actually correct and that the implementation meets the spec. Why does that work in hardware and not in software? Well, the answer is interesting. It's because the cost of getting it wrong is much higher if you're building hardware than if you're building software. If Microsoft makes a mistake and introduces a bug, well, next Tuesday or Tuesday next month, we can fix it and give you a new version with a patch in it that will take care of the problem. Hardware people don't have that possibility. They have to get it right the first time. So they spend a lot more money using these kinds of tools. But as soon as we can convince our software brethren that this is a reasonable thing to do, I think there will be considerable progress in this area. Well, that's an interesting. Oh, I see. The 14th challenge was build a system used by millions of people, administered and managed by a half-time person. And this, of course, is about the efficiencies of large-scale computing of the sort we find in data centers, and it's effectively been solved. We can do it today if we do it, if we give up some of the ideas about management that we had earlier. It turns out the reasons that we don't actually do this are not really technical. They're things like people who run these data centers are very conservative people. When something breaks, they consider it a personal affront, and they have to go in and fix it. And frequently that does more damage than good. It might be better to just leave it broken and suffer the small loss of capacity for a while that engenders. The other problem is, of course, a management problem, which you all know about, which is that managers like to have large staffs. That causes them to get paid more. And so they resist this. But I think technically we've done pretty well on Jim's challenge. The 15th, security. This is all about computer security. And it's probably not possible, as Jim stated it precisely, because in the security loop there are imperfect humans. And it's too easy to trick an authorized user into giving an unauthorized user access to the system. That is generally called phishing, and many of you have received endless amounts of email emanating from Nigeria asking you to help liberate a little bit of money one way or the other, which you will then share. I don't know why they do that. They really believe that people are dumber than they are. The other problem is that unauthorized nation states or well-funded criminal organizations can put a lot of metal behind this arrow, and so it's. I mean, we've seen viruses that probably come from nation states that have caused a lot of damage in the world. But the fundamental problem is that most people prefer convenience over security and, in fact, over privacy. You're annoyed when you have to type your password and you get it wrong the first time and the machine won't let you do something, or when you get a lot of spam. We could stop spam today in 1 minute. If it cost 1 cent to send me a piece of email, I would never get spam again. And why is that? It's because the spammer depends on volume. And he has to send out 1 million spams in order to get one hit on his pharmaceutical product or whatever it is he's peddling. Now, it's easy to send out those 1 million things because, of course, there are a lot of computers out there in the world that he's already taken over because people haven't actually protected themselves very well with things like virus scanning software. But it's definitely an arms race. But we could fix this if we thought a little more and valued security over convenience. Computers have made it very easy for us to do a lot of things. Oh, come on. And the final challenge was build a system used by millions of people that's always available. This is a question of high availability. And Jim was a pioneer in this field. He built systems that were used to operate banks, for instance, bank databases that almost did this, and that was back in the late 1970s and early 1980s. And the techniques that he used, were the same kind of things that the people who send spacecrafts to Jupiter use. They provide 3 computers and they vote on the result, triple modular redundancy. We would like somewhat better than that, and we'd like much larger systems to have this property. He also said, and prove it, which is very hard because it's hard to prove something about something that's fundamentally at its nature, at its root, probabilistic, as opposed to sort of digital. And I think a more realistic challenge might can be a little bit more reliable than the present electricity or telephone system. And that's wired telephone, not mobile phones. Mobile phones have a lot more problems, so they aren't reliable. But at least in the US, the wired phone system did have 1 second per year failure properties, at least until the Bell system was broken up. And I say this is probably adequate because if these things fail, like the phone system and the electrical infrastructure, you've got bigger problems than whether you can access Facebook or not. So, we have done pretty well on Jim's challenges, I think. The only things that we haven't done well on are ones of the sort of make computers intelligent, or do things perfectly and prove it. And as I started out, I'm not sure that is as important as we used to think it was, because it's not important that a tool be perfect. It just has to do a really good job at the tool, as a tool. But we do have some new challenges in the world, and I've thought about 3 of them. One is that computers aren't getting any faster. For a long time we've thought, well, we'll just buy another PC and it'll be twice as fast and we'll be twice as happy. That has stopped, I'm afraid. And so we're just going to have more of them. They're going to be about the same speed. That has a lot of implications for what we do. Secondly, we have a lot more data today than we did, and we have choices as societies about how we're going to use that data. And we have to be very careful about how we exercise those choices. And finally, the supply of skilled IT professionals is not keeping up with the demand. This means that we are going to have a lot more computers, but we're going to have no one to fix them, and no one to manage them, and no one to write software for them if we don't get busy. Last time. So, the individual computer performance. Gordon Moore told us about how transistor performance would improve over the decades. And he didn't actually believe that his prediction, which is that you can put twice as many transistors on a given area of silicon about every 2 years, would hold for a long time. He said for a long time, but it's been 60 years and it's still holding and it's still working. But has not really turned out to be the limit. Another fellow named Denard in 1975 talked about the implications of that scaling, which is that you have to operate the chips at a much lower voltage. And unfortunately today, we've reached the lowest voltage that the physics allows us to run at. And so we can't go any lower. And that means that the power that a chip draws is now determined pretty much solely by its clock rate, how fast it is. So fast computers are hot computers. And we're running out of our ability to remove heat from the chip. Now it stops being a computer problem or an electrical engineering problem and starts being a mechanical and thermal problem. And they're stuck. So we're going to see more computers rather than faster computers. The problem is that we won't be able to use all of these transistors that we get, that Gordon Moore gives us. And so we only have two remaining levers. The transistors are no longer a lever in order to allow us to make progress. We need architectural innovation, and we need improved software. And unfortunately today, both those fields proceed fairly incrementally. And that can't last if we're going to make progress as a society. We have to improve that. Both are improved by better education of IT professionals. And so here are the areas in architecture where we really need some advances. Networking, so that we can actually make use of the thousands of CPUs on a single problem. That's the area in which I work right now. We need lower energy techniques so that we can use the large number of transistors we'll get. Things like asynchronous logic, where you don't actually have a clock, and therefore the clock frequency does not come into the picture. You only dissipate energy when you actually do something valuable. That's a possibility, but it's a very difficult thing to design and get right. Reconfigurable logic, well, possibly, but it has the paradox of, in order to do it, you have to have high volume, and specializing these things is the only way you can get that. Design tools, that's software again. Have to build better design tools to design the hardware. And how to improve teaching? Well, a couple things we've seen recently are things like these MOOCs, massively online courses. Several of those have been done in the U.S. There's an organization in the U.S. called the Western Governors University, which is a fully online 4-credit but paid with tuition university which just graduated its first class. One of the things they offer degrees in is IT. Big data is another challenge. We're getting a lot of it from phones, from surfing, from purchasing, from scientific experiments, and from medical procedures. And the big challenges there are collecting it and preserving privacy. Storing it all, storing it securely, and using it wisely. So McKinsey did a study in 2011 which said that if we could effectively use the big data that we're gathering now, we could save $300 billion in healthcare costs in the US. And of course, as most of you know, healthcare is the biggest problem in the US because we can't afford to pay for the increases. If we could make use of the localization data that you get from your cell phone, then consumers, retailers would get $600 billion of additional revenue, profits. I found that one a little difficult, but they did justify it. And of course, the operating margins go up too. And if we could use that big data intelligently, we'd get a couple hundred, this is in the US, a couple hundred thousand new IT positions and related positions in other areas of business that actually make use of the big data. That amounts to 1.5 million. So it's not huge against the size of the US workforce, but it's a substantial increase. So final thoughts. So we've got a lot of areas that can be improved by IT, and each one of them are a grand challenge of their own. More efficient energy extraction, distribution, and use. Computers actually have enabled us to extend the world's oil reserves by several factors, by better exploitation. Computers run all our factories. Now, in the US, of course, we used to be a serious manufacturing economy, and we lost that for a while, and we're now getting it back. But it's different because we're not doing the kind of large-scale assembly line manufacturing that allowed low-skilled people to get good jobs and build good lives. What we're doing is we're creating a new kind of work where people are needed who can actually program and operate the robots that actually do the kind of work that the American worker used to do and would dearly love to have today. But unfortunately, those 20th century jobs have gone, and they're not coming back. So that's another aspect of education. Improved medicine? Well, one of the things that we could do with that big data is it turns out that if everyone's genome were fully indexed, were fully sequenced, and you could look at all their medical records, you can very frequently derive correlation. So if you look at everybody's genome and you look for anomalies, and then you look at everybody's diseases and you look at anomalies and you match them up, you can actually figure out what causes diseases without ever looking at the symptoms or anything. This has actually been done in a couple of cases, and it's been strikingly effective, even though the number of people who have been fully sequenced and the number of people who will give away all their medical records is now relatively low. But if we could do this, we could probably make some fairly substantial contributions in health, which would be quite good. And of course, all of this, I believe, centers on education. And people tell me that, gee, isn't computer science getting boring? Isn't engineering getting boring? Because we've discovered everything, or because there's no more progress to make. I say nonsense. If you're looking for a field to get into today, with the possible exception of biology, I think that computing is a right thing to do, and I strongly recommend it to you. So I thank you, and I'd be happy to take any questions.
In the beginning, can you hear it?
Yes.
So in the beginning of your presentation, you mentioned how the computers nowadays are limited by physical limits. And the first thing that came to my mind is the development of quantum computers, which obviously have much more processing power. Do you think that the focus should be on developing these quantum computers and pushing the performance of the computers even further in the near future?
Well,
should we focus more on using the resources that we have and kind of increasing efficiency and focusing on optimization?
Well, I think we have to do both, and in fact, in Microsoft we are. We have a fairly substantial quantum computing collaboration with the University of California, Santa Barbara. So we're doing it. Several other people are doing it. There are a lot of difficulties, but we're working through them. But we have to also solve the problems that we have today as well as solving the problems that we'll have tomorrow. So I think a two-pronged approach, or actually a multi-pronged approach, because all that I said today about limitations and speed running out could change tomorrow if some clever physicist found a new effect.
I mean, the problem is more fundamental, because as you approach the physical limit, the binary system will collapse. This is the challenge. The binary system will collapse, and you go to the quantum regime.
Yes, that's right. Quantum effects become more important at small scales.
Because you go to one electron, and then you have no binary system anymore.
That's right. But you can run out of the availability to have a solid 0 and 1 long before that, long before the quantum effects matter. Right.
I mean, this is really the fundamental problem.
Any other questions? Yeah.
First, I have to ask, in the beginning of...
Could you use the microphone, please?
In the beginning of the lecture, you mentioned something about intelligence, and that's defined as speaking on the phone with a computer for 30 minutes, not realizing it's a computer. A, do you think that that's ever going to happen, and if so, when? And B, how will we technically solve the problems that are stopping us from doing that?
Well, it might. I mean, I've actually been somewhat impressed by these deep neural networks and their ability to mimic the way the brain actually works. There are two things that give me some hope. One is that we're actually getting a much better understanding of how the brain works. The neurophysiologists now have much more sensitive instruments to figure out what the brain is actually doing when we think. And that will certainly help. Better techniques of the neural network sort. I mean, there was an article that said that recently in one of the scientific journals that said that IBM had programmed a very large neural network to be approximately as smart as a cat, which I found amazing. And I don't quite believe it. But of course, when they trained it and they set it loose, what did it do? It went out and surfed the web and looked for pictures of cats. We do that too. So maybe there is some intelligence there.
Well, to go to complexity theory, I mean, we know many problems are pretty hard problem we cannot solve. Do you think, are we getting smarter in the future and we'll solve these problems, or there is no hope?
Oh Lord, is P equal NP? Actually, I don't much care, because fundamentally I'm not a mathematician. This is something the mathematicians can worry about. I'm an engineer.
I know, but this probably can't be solved. I mean, point. I mean, are we going to this?
What would solving it do for us? If we knew that all these things that we couldn't previously compute, now we can. It takes 5,000 years or something.
No, I mean, it's not a matter of time. I mean, the value problem is that we know it's like the size of the system, the Hilbert space is infinite size, and it's an exponential with the size. There is no way, there is no hope to solve it.
Oh, I know. And,
so it's not a matter of time. It's really more fundamental.
Well, I used to think that you should never, you wanted to avoid in-cubed algorithms like the plague. And what faster computers did was ratchet us up by one in the exponent. Now I'm frightened by n to the 5th problems. And, I just can't get too excited about that. I mean, they're complexity theorists, but they're theoretical computer scientists, and I'm not one. So I just don't worry too much about it.
I'd like to second the fact that you could do a lot with heuristics and so on and so forth, and bring the problem down to
Absolutely.
some practical space that you can solve, and let the mathematician worry about the equality.
Right. I mean,
No, but I mean, if...
There's a question.
I mean, if a quantum computing can...
Excuse me.
Yeah.
Let me ask the question.
So among the new computing challenges that we listed, was like computers are getting faster. And you said this is the main challenge, and the solution now is that we are getting just more of them. But at the same time, you mentioned the state.
mention.
You mentioned the state and big data and these kinds of things, and you added that we require advances in networking because we have eventually, or we want to collect, we want to network computers together to solve a certain problem.
Right.
Why would then focusing on a single computer, since things do not really fit on one computer, be a big challenge to have that single computer pretty fast?
Well, that's what computer science has been working on for 50 years, is making a better single computer. Okay? And we've run out. We've basically run out of our architectural cleverness. And what we found is that it possibly might be better to strip away some of that complexity. I mean, I gave 2 lectures here earlier in the week where I described how computers actually had evolved over the first 50 years, 60 years of computing. One of the observations is that most of the logic in a present computer goes in not to making, just into making it fast. You can actually solve the problems at, for instance, 1/4 the speed with something that's 1/10 the complexity. And so maybe it's better to back off on the performance of an individual computer and begin to look more at something that we've not looked at very carefully, which is how to harness tens of thousands of them. And that requires better networking. Okay.
So listening to all the trends, the problems that you're talking about, and extrapolating the trends, I couldn't help myself but think manufacturers are going to lose jobs, some doctors are going to lose jobs, drivers, pilots, workers. Do you feel that economics or the fact that computing now is starting to push up this scale of different venues will scare people into adopting these things fast enough? Or, you know, we know how to do electrical cars that have very fast planes, but oil industry, you can name it, are holding these things back. I wonder, at this scale of progress that we're seeing, how that pushback might look like.
I don't think there will be pushback. I mean, people seem perfectly happy to make Apple the largest company on the planet. Okay? People love technology. They're happy to, and one of the things about many of the technologies that I described is you won't see them. They're invisible. They're in your car. You don't think there's a computer in your car driving it. You think your car knows how to drive itself. Okay? One of the most successful uses of computers in the United States is actually not really thought of very much. It's the ATM machine. Okay? You go to this machine and you do a little simple incantation and it gives you money, or it does all your banking transactions. Nobody thinks about that as a computer, and yet there's a tremendous network of computers down there doing very cunning things to do all that. People won't think about most of their computers as computers. They'll think about them as things that help them do their jobs.
And that led to a lot of jobs. Tellers have lost jobs because of that.
Right, and I'm afraid that many of the very low-skilled jobs that there are will disappear. And that's going to be a problem, and we're going to have to deal with it. But, you know, maybe there'll be a lot more people on whatever the 21st, 22nd century equivalent of welfare is. I don't know.
The interesting thing is, society, there are many jobs that used to be there in 19th century that are not there.
They're gone. I mean, after all, 50% of the United States employment were farmers.
Global wealth has increased with better technology.
That's right. It's been-
It's clear. Some of you, I know you have classes to go to at 1 o'clock, maybe one more question, and then after we have a light lunch, you could still talk to Chuck, of course.
Right, I'll be around.
So I noticed that overall you're very optimistic about the challenges you laid out in terms of the progress that's been made. But when it came to both security and availability, you seem to be more pessimistic about the achievability of them. I'll say. I was wondering what about those problems makes them
Well,
less optimistic.
I'm optimistic about the ability of human beings to solve problems, but I'm a little pessimistic about human beings being willing to sacrifice convenience for some of these other things like security or privacy. But on balance, and you might argue that it doesn't matter. I mean, Scott McNeely, who used to be the president of Sun, said, "You worry about privacy? Don't worry about it. You never had it, you never will." And we're happy to put up with surveillance cameras on every street pole, on every light pole. So perhaps we'll come to a compromise that said, I value the fact that my medical record kept me alive 10 years longer than it otherwise would have because it was more available and less protected by some privacy wall. I don't know. I mean, that's something that societies will have to figure out.
Thank you, Chuck.
My pleasure. Oh, thank you very much.
You're welcome to join us for some refreshments and light lunch. And thank you for being here.